Well, thank you for Professor Martin for that introduction. I'll try to live up to it. I was going to say that I was happy to see so many of you decided to take a chance on a seminar with such an unusual title, but then I heard that this is actually a class and that you pretty much have to be here. I'd like to thank the department also for inviting me to come here. One of the pluses for me for traveling anywhere these days, actually, believe it or not, is getting to ride on an airplane. I know for most people, air travel is a chore, but for me, the actual airplane ride part of it has never gotten old. Yesterday, for example, flying from Seattle to here, I had a window seat over the wing, which I usually don't like because I can't see as much then, but it did give me a chance to see again something that I've seen many times, and that's the sun shadow graph visualization of the shock on the upper surface of the wing. I don't know how many of you have seen that, but to me it's always an exciting thing to see that all of this stuff that I've seen in pressure distributions from the wind tunnel and from CFD actually happens in flight, and you can actually see it with your own eyes. That 737 that I rode on yesterday actually reliably generated lift approximately equal to its weight all the way from Seattle to Detroit. And lift is a subject that is still worth discussing, and I'm going to get into that a bit later. So, as Professor Martin mentioned, I've worked on a lot of different things in my professional career, but throughout all of that, I've had this kind of preoccupation with basic physics. My undergraduate degree is in physics after all, and so I've always had this interest in being able to explain things to myself in intuitive physical terms and to get things right, that is, not fall prey to misconceptions. So that's what I picked for my topic to talk about today, misconceptions in aerodynamics. What I'm going to cover is a collection of erroneous ways of looking at aerodynamic flows. These mostly have to do with the basic physics, basically misinterpretations of the actual physics of a flow. For each of these cases, I'm going to try to put my finger on what went wrong in each case and what you have to do to set it right. Back when I had to send the abstract for this talk and I hadn't written the talk yet, I promised I was going to identify some common threads. Well, what I finally arrived at in that regard isn't as much as I thought. I think you'll see the common threads are a little bit thin, but I'll try to do that anyway. And most of these examples are in my book, although not necessarily with the same spin as I'm going to put on them today. So Professor Martin's already made a shameless plug for the book. It came out in December, and it's now available at a bookseller near you, so I won't belabor that any further. Why look at misconceptions? You might think that this is a sort of exercise in schadenfreude, big word, but fairly simple meaning. In this case, taking pleasure in chuckling at mistakes made by others. And I'll have to admit that actually that is part of the fun of being an aerodynamicist, but I'm going to maintain that there's a positive purpose as well, and that is that if you really work through a rigorous debunking of some misconception about the physics, you're almost sure to find that your own assumptions get challenged. And if you work through all of that successfully, it can't help but strengthen your understanding of the correct explanation when you finally get there. So here's an outline of what I want to try to get at. Since these are mostly things having to do with misinterpretations of basic physics, I'm going to take a few minutes in the beginning to actually talk about the physics that we're dealing with, so we'll know what the misconceptions are relative to. And then I'm going to talk about Newton's third law, and I'll actually dwell on that a bit more than I did in the book, because I've become convinced lately that there are a lot of conventional explanations out there that pretty seriously abuse Newton's third law. Lift explanations are, of course, with regard to finding misconceptions, lift is easy pickings. setting the misconceptions right is not quite so easy, and I'll get into some of those issues. Another really rich vein of these things is vorticity and the use of the Biot-Savart law, and I'll cover a couple of examples of that. We'll get into how lift impacts the motion of the atmosphere at large. There are several misconceptions around in that regard, and they're not necessarily just intuitive physics-based. They can actually, some of those actually result from misinterpretations of the mathematics. I've got quite a long list here. I'm proposing to also talk about boundary layer separation in 3D and some issues regarding pressure drag. But as I say, the list is a little long, and if I make it through lift and momentum in 3D, I can skip over the other ones if we have to in the interest of time. So the basic physics. This is continuum fluid mechanics. I'm not talking about flight at extreme altitudes or anything like that. The fluid is, of course, not a continuous material, but it flows as if it were one. The velocity is a continuous vector field, and that by itself tells us some pretty powerful things that constrain what the flow can and can't do. There are kinematic rules that have to be obeyed, and so we have a lot that we can say about the flow even before we get to the dynamics. The dynamics we're talking about are essentially what I call the Navier-Stokes equations, or the Navier-Stokes equations if you went to private school. And I take that term to refer to the whole equation set, not just the momentum equations. Some people apply it to just momentum. The momentum equations essentially are enforcing Newton's second law, F equals ma. We use classical thermodynamics to impose an energy balance, conservation of energy in the energy equation. These are all concepts from classical physics, where we have mathematical equations, of course, but there's more to it than just equations. The equations actually represent some clear cause and effect relationships. We're not in the realm where we have quantum weirdness or any of that going on. This is strictly classical physics. Applying F equals ma to a continuous material takes a little bit of extra mathematical manipulation. To deal with the acceleration of the fluid, you have not just the unsteady term, the dv dt, but you also have to deal with a term that we call a convective acceleration. Forces are transmitted between parcels in the fluid by what appear to be internal stresses. These are really the result of momentum transport by molecular motions relative to the continuum flow. But they have the same effects as if a continuous material were under internal stresses. So this is the pressure and the viscous shear stress. We formulate these terms in a way that automatically satisfies Newton's third law. That is, the formulation automatically enforces a condition that the force exchanged between two fluid parcels across their common boundary is equal and opposite. These are, of course, surface forces. We ordinarily neglect body forces. Gravity, for example, we simply omit from the equations, assuming that that's going to be balanced by a hydrostatic pressure term that we also leave out. And then the interaction of the fluid with other things, like a solid surface, requires an extra bit of physics that is not inherent in the equations themselves. And for ordinary fluids and ordinary materials, the way that interaction works, it's very accurately approximated by a condition of no slip and no jump in temperature. So the consequences for all of this for flows around bodies, fluid flows are not a hail of bullets like Newton assumed they were when he tried to calculate lift. The fluid has to deform and flow around obstacles rather than fly directly into them. We have forces that are transmitted only by contact between adjacent fluid parcels, and we have no action at a distance taking place. And we'll see later that actually this action at a distance thing has been a source of some misunderstandings. So we can move on to what I call stretching, the stretching of Newton's third law. My first example here is from the Smithsonian website, and here they're talking about rocket propulsion, and they're using the example of a toy balloon that's been inflated and then it's been released to fly around the room like a compressed air rocket. And so I'll read it here. The air coming out the back of the balloon is the equal and opposite reaction to the thrust. Well, not really, not in the sense that Newton intended when he put forth the third law. For every action, there is an equal and opposite reaction. When Newton used those words, or what translates from the Latin into those words, by action and reaction, he just meant force. The third law actually isn't about motion at all. It's only about forces exchanged by bodies. Another example from a NASA website about propulsion systems, and this one says that all thrust is generated through some application of Newton's third law of motion. Well, again, it's true that a fluid and a body exchange equal and opposite forces across their interface. But just saying that doesn't really tell you anything about how that force actually comes about. It doesn't say anything about how the fluid can actually exert a force on a body. Generating an aerodynamic force generally requires the fluid to be accelerated somehow. And acceleration and force are the domain of Newton's second law, not the third law. So all of these were kind of examples of this kind of general conclusion I've reached, and I don't really come down as heavily on this in the book as I wish I had, that Newton's third law by itself really isn't very helpful in most situations. It's obeyed, of course, but it doesn't really tell us anything. We have these sort of generic sorts of explanations that people put forward. A rocket pushes on the gas and the gas pushes back, therefore we have thrust. Wing pushes on the air pushes back, and therefore we have lift. An explanation of this kind really doesn't tell us anything about how the fluid generates the push. To understand that, we really have to get into the down and dirty sort of details of the fluid flow field, accelerations out in the field. And of course, as I said before, the key is Newton's second law, not the third law. Explaining a flow field phenomenon fully and correctly requires getting into some details of a continuum flow field, this phenomenon that's very spread out, not that easy to understand intuitively. And so, needless to say, this has been a source of a lot of misconceptions and misunderstandings through the years. I think the poster problem for this, or the poster child for this problem is aerodynamic lift. Physical explanations of aerodynamic lift have been a problem for the last 100 years or more. And I just love this quote from my Boeing colleague, Philippe Spilart. This is from an email he sent to me a few years ago, and I think it really hits the nail on the head about how difficult lift is to explain. It also gets in a little bit of a dig at some current popular culture terminology, and that is, why is it that if you design airplanes, you're called an engineer, but if you design rockets, you get to be called a scientist? It doesn't seem quite fair to me. Anyway, explaining lift is more difficult than people realize. It's generated a lot of misunderstandings, a lot of and resulting controversy. So, to start off, I've been involved in some online discussions in recent years of this problem where people really get into the details, and some of the arguments get pretty heated, but people really do get into the details of this problem and try to work it through. And then I've seen it happen several times where someone new will join the conversation and say, wait a minute, why is everybody making such a complicated deal out of this? Lift is just a pressure difference, or lift is just Newton's third law. Why are you making it so complicated? Well, we're making it complicated because these explanations are simply inadequate. They don't explain much of anything. The most popular explanations get into a little more detail, and they tend to fall into one of two categories. The Bernoulli-based explanations and the explanations based on downward turning of the flow. So I'll go into those a little bit to show what their shortcomings are. In the Bernoulli-based explanations, we say that faster flow over the upper surface results in lower pressure, and therefore you have lift. So you need to have that higher speed over the upper surface to get where you want to go. You can't use the lower pressure as the reason for the higher speed because that seems like it's roundabout. So you have to come up with a reason for the faster flow. And two main approaches to that. The longer path length and equal transit time, which is really bad, and the stream tube pinching and conservation of mass, which is not quite as bad, but still not good. The longer path length and equal transit time. First, the transit time isn't really well defined. In a viscous flow, we have a no-slip condition, or we assume a no-slip condition at the surface. So if you look at fluid parcels traversing the airfoil closer and closer to the surface, the transit time goes to infinity the closer you look. Even if you want to look at a potential flow, if you have an airfoil with a rounded leading edge and a stagnation point, you have the same problem. The closer you look to the surface, the larger the transit time is. Okay, you can get around that problem. You can gloss it over by saying, well, I'm going to follow fluid parcels that traverse the airfoil a little ways off, say outside the viscous boundary layer. So let's say we get around it that way. The typical difference in path length between the two surfaces is typically an order of magnitude, roughly an order of magnitude too small to explain the actual observed lift. So if you take the path difference in equal transit time as a theory of sorts, the theory misses the mark pretty badly. And the problem is that the equal transit time assumption is simply wrong. If you look at these fluid parcels that start together on the attachment streamline, they finish permanently shifted from each other. That is, the parcel that traversed the upper surface gets there in a significantly shorter time. Stream tube pinching starts with the statement that the stream tubes that pass over the upper surface are pinched more than those that pass over the lower surface. Therefore, the velocity is higher through conservation of mass, and therefore, with Bernoulli, we have lower pressure, and now we have lift. The common problem with all of this is that the pinching is just assumed, or it's justified by pointing you to some smoke flow visualization pictures or CFD or something. But I haven't come across one that really explains why the stream tubes pinch at all, let alone why they pinch more over the upper surface than they do over the lower surface. I go through a little exercise in the book where I show that there are kinematically possible flow patterns that don't have any pinching at all. So if you want to explain why pinching happens, you have to get into the dynamics, which this kind of explanation typically doesn't do. And my final complaint about this is that mass conservation really isn't a very direct physical reason for an acceleration to happen in the flow field. Newton's second law says that an acceleration requires a force. So if something accelerates and you want to explain to me why, tell me what the force is. These explanations don't do that. So, common fault of these Bernoulli-based explanations is that they don't use the real direct reason for the higher speed, which is the lower pressure, because they want to explain the lower pressure. So they end up going to indirect reasons like stream tube pinching or incorrect reasons like equal transit time. And implying that the causation between speed and pressure is a one-way street, that is, that the speed results in lower pressure, is a misconception. So the downward turning based explanations. You just say that the flow passing by the airfoil gets deflected downward through a combination of airfoil shape and angle of attack. Turning the air downward is an acceleration, and to produce an acceleration you have to exert a force. So you say the airfoil must push down on the air. That's a Newton's second law thing. And then, of course, with Newton's third law, you say the air has to push up on the airfoil, and you have lift. Some of these explanations point out that the downward turning action is contributed to significantly by the fact that the air over the upper surface follows the convex surface and actually gets directed downward as it goes over the aft part of the airfoil. And then they suppose that in order for air to follow a convex curve, there has to be something like a Coanda effect or some viscous effect involved. Okay, most of these things deal only with the interaction that takes place at the airfoil surface. That is, the airfoil pushed on the air and the air pushed back. They don't satisfactorily explain how downward turning gets imparted to a lot more flow than the airfoil actually touched. And the fact is that viscosity and the Coanda effect are not needed. Flows follow convex surfaces just fine without either of those effects. I've also seen it put forward sometimes that actually only a 3D wing turns the flow downward with all that downwash between the trailing vortices, and that in a 2D airfoil flow there really isn't any net downward turning because the vertical velocities involved go to zero at large distances from the airfoil. So you get far enough away from the airfoil, there hasn't been any downward turning. Well, that's only true when you look at the velocities locally. Yes, they do go to zero at large distances, but the distribution of vertical velocities also gets much more spread out, and the integrated effect, that is, the integrated fluxes of momentum, are actually constant and don't go to zero. So in an integrated sense, there is actually downward turning in 2D. If you look at a control volume like this with two vertical faces, you find that with an airfoil with circulation around it, there are fluxes ahead of the airfoil and behind. That is, a flux of upwash ahead of the airfoil and a flux of downwash behind that account for half the lift each. And then you can say, well, the airfoil is what imparted the difference between those two, and that accounts for all of the lift. And this is a result we're going to see later also applies in 3D. Okay, having two explanations, Bernoulli-based and downward turning based, that sound so different has really been a problem for a lot of people. How can the same phenomenon be explained by two such different sounding things? And you get some people who say that only one or the other can be right. You get other people who say that both are right, and they're just equivalent ways of looking at the same thing, and which one you prefer is just a matter of taste. Actually, each one of these is partly right, but incomplete. And my position is that a complete explanation needs to look at both. The Bernoulli explanation deals with the speed of the flow outside the boundary layer and with the surface pressure, so that's all very near field stuff. The Newton explanation deals with the flow direction over a much deeper swath of the flow and is more sort of far field stuff. These are not contradictory, they're really complementary aspects of the same phenomenon, of one single phenomenon. And I don't think it's really fair to say that they're equivalent ways of looking at the same thing. They're ways of looking at separate parts of the same thing. So to get it right, as I said, I think a correct, complete explanation really needs to have elements of both the Bernoulli approach and the downward turning approach, but it also needs to emphasize some other things that are either glossed over or completely neglected in the conventional explanations. For one thing, I think we need to put a lot more emphasis on the fact that the fluid is flowing as a continuous material, and that therefore the velocity and the pressure are affected over a very wide area around the airfoil. So we have, of course, the downward turning and that being imparted to a deep swath of flow. We also have the pressure disturbance spread out well into the field. The pressure difference between the upper surface and the lower surface is not confined just to a region very close to the surface. It's spread out over quite an area of the flow field. we have this sort of diffuse cloud of low pressure over the upper surface, diffuse cloud of higher pressure under the lower surface, and these clouds of pressure difference, of course, involve gradients in both directions. We have significant pressure gradients in both the streamwise and the cross-flow directions. So we really have to be talking about both a Bernoulli and a Newton approach to explaining this, or Newton in a vector sense. The other way to look at it would be we're talking about trying to explain the interaction between the velocity field and the pressure field that's embodied in the Euler equations. This is really more an Euler explanation of lift that I think we have to go to. Another one, the cause and effect relationship between the velocity field and the pressure field is not a one-way street, it's a reciprocal or mutual interaction. Of course, we have the pressure field being the direct cause of all the accelerations in the field, at least outside the boundary layer. This is Newton's second law. And this is the little bit more difficult part to grasp intuitively and to explain. But the pressure field is sustained by the fluid's inertia and the acceleration. So this piece of it, because it's harder to grasp intuitively, is kind of the weak link. It's the part that in the explanation that I have in my book is the part I'm least satisfied with. It's the weak link. Mathematically speaking, we can say, of course, that the pressure arises as part of the solution to a set of field PDEs with multiple variables. Physically speaking, we know that motion around an obstacle is non-uniform. It requires a non-uniform pressure field. A pressure gradient can exist only if something pushes back, and that's a statement that you won't see in any fluids book, and I've had people push back on me on this one. But it really is just a consequence of Newton's third law. If a pressure gradient exists, it's exerting a net force on any fluid parcel that's submerged in it. And Newton's third law says that that push, that net force on the fluid parcel, has to be opposed by some equal and opposite reaction. That pushback is provided by the inertia of the fluid and the fact that it's being accelerated. Okay, if any of you read the book and look at how I go through this in the book, I'd appreciate it if you'd give me feedback on how to strengthen that part of the explanation, because as I say, I think that's its weakest link right now. So I've gone through a quick outline of what I think are the ingredients in explaining lift. The actual embodiment of this in an explanation is in the book, and I'd urge you to look at that. Okay, another rich vein of misunderstanding is the vorticity field and the Biot-Savart law. The Biot-Savart law is, of course, just a mathematical equation. It's essentially a bit of vector calculus. It doesn't have any physics in it. It just arises from the fact that the velocity field is a continuous vector field. If we look at the vorticity vector omega, which is just the curl of the velocity, we can use this integral formula to calculate at least one part of the velocity field. So here's the situation. We calculate the velocity at some point x, y, z by doing a volume integral over the entire space surrounding it. Basically, the volume integral of omega cross r over r cubed. This is the form that's valid for vorticity distributed throughout a volume. There are a lot of situations where the vorticity is fairly concentrated, like in vortex sheets or vortex filaments, and there are forms, idealized forms of the formula that apply to those situations where you assume that those concentrations are very thin. You can reduce the triple integral to a single integral for a vortex filament, for example. Okay, the difficulty arises here because here we have a formula that's very useful for computation and for theorizing about wings and so on, but the vorticity vector is the input and the velocity is the output. And it leads to the idea that the vorticity is somehow causing the velocity to do stuff elsewhere. And the analogy with electromagnetics doesn't help. Essentially, in electromagnetics, we have the same formula, at least in the steady state, where the electric current here is the input and the magnetic field there is the output. And that really is called induction. And that really is a physical action at a distance kind of cause and effect relationship. And so we carry that thinking over into aerodynamics, and we even say that the vorticity induces the velocity. Of course, this is wrong. It's implying that the vorticity is causing things remotely, which it's not doing. Okay, the first example I'd like to use of where this has led people astray is drag due to lift in 3D. Here's a cartoon of the flow field that a wing causes a lifting wing as it passes through the atmosphere. We have this is illustrated in terms of velocity vectors in a cross plane. So we have this general pattern of circulation around the wingtips, downwash between the tips. This pattern gets pretty well established at the station of the wing itself, and then it tends to persist over very long distances downstream from there. It's associated with a shedding of a vortex sheet from the trailing edge of the wing and a rolling up of that vortex sheet into discrete vortex cores downstream. And that's the part that really leads people astray because it's really convenient, and a lot of the theories make use of this. It's really convenient to look at that vorticity distribution and use it through Biot-Savart to calculate what this flow field does. And that's what we do in a lot of the theories, and it leads people to think that this flow field is a result of that vorticity that gets shed. Whereas the reality is that the vorticity is there kind of as a trace of what's happening. It's not a cause. So people get the idea that this flow field is caused by the vorticity distribution. This downwash across the span of the wing, of course, results in a tilting back of the lift vector and results in what we call drag due to lift. And so we end up even calling it induced drag, which is, I think, a misnomer. And people get the idea that induced drag is caused by the wake vorticity. And that leads further to the idea that, people with inventive minds get going with this. And they think, well, if I could just eliminate some of that vorticity, catch it right after it was shed so that it doesn't get into the far field, I can reduce the amount of the vorticity that I have to integrate over in Biot-Savart. I can decrease the downwash at the wing, and I can reduce the induced drag. So the vortex sheets that come from the trailing edge and the resulting rolled up vortex cores are relatively compact structures. And this further leads people to think that a device that would eliminate that vorticity doesn't have to be very big. It can just operate on a little bit of the flow, and I can have a big effect on the flow. That's what Biot-Savart tells me I should be able to do. So there are numerous inventions that have been proposed to accomplish this. And when I wrote the book, I was going to use drawings from a lot of patents to illustrate it. But of course, I would have to get permission from the inventors to use those drawings. And the first one I contacted, for some reason, was reluctant to give me permission to use it in a book that was going to say that his invention was worthless. So I made a generic cartoon. There aren't actually any devices that look exactly like this, but this is sort of the basic idea on which they all operate. The idea is you try to catch some of that vortical flow before it gets into the far field and eliminate the vorticity from it. So here's one way that you could do that according to the thinking of inventors of this sort of thing. You have this sort of thing that looks like a fan cowl. It captures not a very large stream tube. This is a plan view of the wingtip. You capture a stream tube that contains a lot of the shed vorticity because it is very heavily weighted toward the wingtip. You capture it into this device and put it through a flow straightener and take the vorticity out of it. And now you've greatly reduced the strength of the trailing vortices, and you integrate over no trailing vortex instead of a lot of trailing vortex, and you get almost no induced drag. The problem is it doesn't work. There are two levels of how you should look at why it doesn't work. The first is the causation thing that I've already talked about. right? Vorticity doesn't cause velocities to happen elsewhere, so you shouldn't be able to control velocity way out there, say way inboard on the wing, by tinkering with the vorticity over here. But of course this raises the question, if you could eliminate the vorticity from that stream tube, and Biot-Savart is true, which it is, why isn't the whole flow field changed as a result? The problem is with this word if. In actuality, you can't actually eliminate the net vorticity. It's a matter of kinematics, actually. To eliminate it, you'd be violating some kinematic laws. You can't eliminate the net vorticity locally without changing that global flow field first. If I go back, look at this device, or go back even further and look at this pattern, right? If you haven't first changed this global flow pattern, then there's still circulation around the region where you're taking out that vorticity. The circulation is still there. You can eliminate all the vorticity from the stream tube that goes through the device, but it's a kinematic requirement that matching vorticity is going to get generated in the external boundary layers on this device. And you haven't eliminated the net vorticity, you've just kind of moved it around a little bit. You've eliminated it from a central core. It's reestablished itself in an annular tube around that core, and it's still there. Okay, so conclusion. If you want to reduce induced drag, you have to do something to that large spread out global flow field, which means you have to do something about the force field that produced it, which is the pressure field. And to do that, you've got to change the span-wise distribution of lift on the wing in some major way if you want to have a major impact on induced drag. Okay, another one having to do with induced drag, and this one also has to do with propellers. This is from a 1984 AIAA meeting paper analyzing the effect of mounting a propeller at a wingtip for purposes of reducing induced drag. So this is a drawing that illustrates only the effect of the propeller here on the left side. Presumably the propeller on the right side would produce the same effect. They'd add together and you'd get double. So a propeller slipstream is a stream tube in which the flow is all swirling. It's all rotating in one direction, consistent with the direction of rotation of the propeller. And it's kind of intuitively obvious that a stream tube with lots of swirl in it also must have net vorticity in it, net axial vorticity. How could it not? So the author of this paper used a solid body rotation model for the velocity distribution in the propeller slipstream, and that's not a very good one, but it's not outrageous either. It's a lot of the pioneers who developed theories of propeller flows actually used that model. So a solid body rotation has a net vorticity to it. If it has a net vorticity in the stream tube, then there has to be velocity induced outside that stream tube, looking like this. So you get upwash, if you've got the right propeller rotation direction, you've got upwash induced across the whole span of this wing and a reduction in induced drag. The problem with this is that the assumption of non-zero circulation in a propeller slipstream violates Stokes's theorem. You can't do that. And to see that, you're going to have to follow my pointer here. Imagine a closed contour encircling this whole propulsion stream tube, the whole propeller slipstream, somewhere downstream of the station of the propeller, and then attach a capping surface to that closed contour. So the capping surface is like a balloon. It's been blown out and bulges out ahead of the propeller everywhere. So the only vorticity in this flow field is in the slipstream, but I've put a capping surface out here that doesn't cut any of that. In other words, there's zero flux of vorticity through that capping surface. Now, Stokes's theorem says if there's no flux of vorticity through a capping surface, then the circulation around the closed contour that bounds that surface has to be zero. A propeller slipstream cannot produce any net circulation. So this paper ended with a little summary of a wind tunnel test that was done to evaluate this idea. It said that there was a drag reduction observed, but it was considerably smaller than what this model predicted. So that's good. Just to justify the idea that this swirling stream tube behind a propeller can actually have zero net circulation, I've plotted some velocity results from Mark Drella's QProp code. These are circumferentially averaged for an optimally loaded propeller on and on. But here's the circumferential velocity. You can see it is indeed all in one direction. The axial vorticity in a slender stream tube like this is dominated by this term here, the 1 over r partial with respect to r term. And I've plotted that here, and I've weighted it by r so that you can eyeball integrate it. It's an axisymmetric integration after all. And I think you can see that, yeah, the integral there is 0, as Stokes's theorem says it has to be. Okay, let's move on. I'm kind of getting close to running out of time here. Let's talk about the atmosphere at large and the manifestations of lift in that atmosphere. The first part of this I'd like to talk about is what I call a Tref's plane slice. That is a slice of atmosphere behind the airplane. The airplane's generating lift L. It spent time T flying through that slice. So it imparted a mechanical impulse, LT, to that slice, and you'd think, well, there has to be a change in momentum. There had better be some downward momentum in this slice corresponding to LT, proportional to L anyway. So the classical approach to this, and this is done in several of the classical books, is to use the vorticity distribution, the wake and the bound vortex on the wing, and Biot Savart, and infer what the velocity field is and do the integrals. So the classical argument is, well, if I wait long enough, the airplane is far away, and I can neglect any contribution from the bound vortex at the wing. All I have to integrate over is the trailing vortex pair. And this is done in several of the classical books. Thwaites' book is one of them. And if you do that integral like this is the integral of the vertical velocity W, and you integrate vertically first and then span-wise, you get this answer. It's proportional to L. It's exactly what everybody expected, and so nobody questioned it, and they published it in their books. Now, my Boeing colleague Larry Wigton is a mathematician by training, and he was going through this classical theory back in the 1980s, and Larry's the kind of guy who doesn't just take something for granted. He goes and he does all the derivations himself. So he repeated the integration, but he changed the order of integration, and he got 0. Now, if I did that, I would just assume I made a mistake and I'd go on, but Larry isn't like that. If you get a different value for a double integral, when you change the order of integration, it says the integral doesn't exist. And in fact, Larry applied other tests of integrability, and sure enough, that function's not integrable. The function W just doesn't die off fast enough at large distance for the integral to exist. So Larry said, well, all right, no airplane's ever flown for an infinite length of time, so I'll take the expression for trailing vortices of finite length. That integral exists, the value is independent of the order, and the answer is 0. So the flow field associated with this trailing vortex pair doesn't contain any net downward momentum. So where is the downward momentum that you'd think has to be there? So Larry went back and reevaluated the assumptions that you can ignore the bound vortex. And he did those integrals, and he found, well, there's an integral of upwash ahead of the airplane corresponding to half the lift, and there's an integral of downwash behind the airplane corresponding to the other half. And this is exactly the same result that applied in 2D that we all saw before. And it's just a simple matter of doing the integrals to show that this applies whether the flow is 2D or 3D. Let's move on and look at momentum accumulated in the atmosphere. Seems like if an airplane has been in the air for time t, lifting with lift L, there should be downward momentum in the atmosphere equal to LT. So Larry set that problem up. You model the vortex system as a rectangular loop, a bound vortex, 2 trailing vortices, a starting vortex. The atmosphere is infinite. The integral doesn't exist. the downward momentum in the atmosphere is indeterminate. Well, Larry said, well, okay, nobody's ever flown in an infinite atmosphere. There's always a ground plane. So you put the ground plane in and you do it for a semi-infinite atmosphere, and the integral exists. The answer is 0. There is no downward momentum accumulated in the atmosphere. Well, that result's consistent with a classical picture from Prandtl and Tietjen's book that shows the pressure being reacted as an overpressure on the ground. If you had it both as an overpressure on the ground and as momentum in the atmosphere, that would be double bookkeeping. It's also consistent with conservation of mass, as Lanchester pointed out in his 1907 book. So this is a figure from Prandtl and Tietjen's. You get this sort of bell-shaped distribution of overpressure on the ground plane. And actually, this is just kind of a special case of some control volume analysis that you can do for what I call pancake control volumes. That is, control volumes that are small vertically compared to their horizontal extent. For that kind of control volume, if you do the free air case, where the ground plane is far away compared with any dimension of the box, you get an overpressure below the airplane corresponding to half the lift. You get a deficit above the airplane that accounts for the other half. If you put the ground plane at the bottom of the box, this is getting us essentially the Prandtl and Tietjen situation. It doubles the disturbance on the ground plane, and it corresponds to half the lift. The disturbance above the airplane doesn't go away in this case locally, but the integral does. And it's surprising. It looks a little bit like it does in the free air case in the center. But remember, this is an axisymmetric integration, and what happens far away matters a lot. And there is a slight positive pressure distribution at large radius that actually drives this integral to 0. Okay, I think I've just about talked myself out of time here. I was going to talk about the problem with using the 0CF criterion for deciding where separation happens in 3D, and proposing that you can't use a local criterion like this in 3D flows. It only works in 2D. And I was going to talk about it through looking at flow patterns like this. The conclusion is that finding separation in 3D actually requires looking at the global flow pattern. There is no single local criterion you can apply. You actually have to look at a map of the global flow pattern and look at what's happening there. And I talk about a region of origin concept and how separation is a line of near discontinuity in the region of origin of the skin friction lines. If you want to get a more detailed description of that idea, you'll have to look in the book. And with that, I'm going to open it up for questions because I've used up all the time.
Thank you.
You're welcome.
Aviation is the largest manufacturing export of the United States and generates about 3% of the world's GDP. So it's economically important. And since now I work